Hello students, so today we'll be talking about this temperature independent reference circuit, but before that I just want to summarize what we have learned in the last class. So we started with the discussion of simple current mirror, and we just had this structure, and based on this structure one could define the value of I out as the geometric ratio of M2 by M1 with the I reference. Okay, so we found that this I out is independent of the VDD. And the next question was how to generate this I reference, right? And later what we did is we made use of a simple resistor like R1, and then we tried to generate this current I reference, and the value of this I reference, which is could be written as something like VDD minus the VGS of M1 transistor divided by R1 would give us the value of this I reference, and that is how we evaluated this uh, I reference. And we just want to know about the sensitivity of this circuit uh, whenever there is a variation in this supply. So when we do so, we just add a small wiggle around this VDD, and that in turn resulted in a small signal current which is written as delta I reference. And we just use a simple small signal analysis here in order to evaluate that current delta I reference. And in a way we try to model this transistor M1 in terms of small signal resistor. So since because this M1 is a diode connected structure, we had a resistance value whose value was given as 1 by GM1. Okay. So based on this, we just got the value of delta I reference that is equal to delta VDD divided by R1 plus 1 by GM, and one could evaluate the delta I out as again the geometric ratios between those M2 and M1 structures multiplied by this I reference that we evaluated. Okay. So in both the cases what we found is that this delta I reference as well as this delta I out certainly depends on this variation of our change in the supply. Okay. And so we want to eliminate this dependency of this delta I reference as well as delta I out that depends on this supply. So in order to do so, we just postulated a kind of structure where we want this particular structure, that is the combination of R1 and M1. We want the current that is flowing through the circuit has to be generated, or the basically we want this I reference to be generated out of the I out itself. Okay, we want the circuit to bias by itself, and that leads to a circuit which is something like this, where we try to replace this R1 structure, okay, with this whole bunch of structure here, and we so this M3 and M4 combination is nothing but a simple current mirror structure that has been made use of the PMOS transistors, and we also ensure that these transistors are being sized in such a way that the M1 and M2 are related by a K factor, and even this M3 and M4 are related by the same K factor. So we sized in such a way that the current of I out is defined as K times that of the I reference, and all of these assumptions are valid under the assumption that the lambda of all the transistors is considered to be at 0. Okay, so in such situation I could end up having this kind of relation, but there is a flaw in this particular circuit. Even though this current delta, sorry, the current I out is completely independent of any VDD supply, still there is some sort of flaw. The flaw is that this I out can, or I reference can support any current value. Okay, so which means that it can support 10 microampere, or it can support 10 milliamperes, or whatever the current that you define it can support. So but what we need as a designer is to have a specific value of current to be flowing through this I out. Okay, so we want a unique value being set in a controlled way, and that is what we wanted out of the circuit, not like a random value that the circuit goes and gets stabilized to a particular value. Okay, so we want to predict those values, and we want to control those values of I out that we intend to have it. Okay. So based on this, we just try to introduce two modifications onto this circuit. One is by adding a resistor Rs across the M2 transistor. So this is one of the modification, and the second modification is to change this W by L factors of M3 and M4 to have the same. So which means that I have to have this M3 right now as the same aspect ratio of that of my, sorry, here I wrote it as, yeah. So sorry for the error that I had before. The M4 is basically a PMOS, so it's supposed to be W by L of P, but I wrote it as W by L of N. Okay, yeah. So the next thing is that we just try to have this relation, that is the W by L of 4 as well as W by L of 3, both will have the same aspect ratio of W by L of P. So we removed this, we made this K factor to be equal to 1 for only for the mirror structure of M3 and M4. Okay. Now having done all these modifications to the circuit, we end up having this kind of circuit, and we call this circuit as a supply independent biasing circuit. And let me prove that why it is known as a supply independent circuit after doing an elaborated derivation. Okay. But before that, we will just see what modifications this, like, let us see how does this modification impact our current equations and stuffs. Okay. So basically when we have this W by L factor for PMOS transistors to be same, then it forces the I out to be equal to I reference. Okay. So it is no more that the value of I out is K times that of I reference, but right now because of this similar aspect ratio, we have this kind of relation. Okay, that is the first modification. The second modification is that when we add this resistor Rs into the circuit, we ended up having a relation which is VGS1, that is the VGS of our M1 transistor is basically split into two components. One is the drop across the VGS of M2 plus the drop across the resistance Rs, and due to which one could write this particular equation. Now after doing all this manipulation, one could write this expression for this I out to be equal to this quantity. So hope that you're clear in this particular case, and the only thing is that in order to tell that this particular circuit is supply independent biasing circuit, we have to look for this expression of I out, and we could see clearly this I out expression is completely independent of any VDD supply. Okay, and that's the reason why we could say that this particular circuit or the previous circuit where we didn't have any resistance or the aspect ratios were being having having a K factor. Okay, so in such cases even we never had any dependency on the value of VDD, right? Yeah. So now that I have to speak about a little bit about the working principle, because at the end of the class I guess I was a bit rushing and to complete the class, so I'll just restate whatever I spoke in the previous video. So what we did is that we just took the same circuit, just this particular circuit, and let us assume that there is a small amount of current I out, or basically the I reference. So this is my I reference, and the ID2 is nothing but my I out. Okay, yeah. So let us assume that we have some sort of small amount of current ID2 is flowing through the circuit, and we mark that particular current ID2 as some sort of small single value. And when this I out is flowing, because of this M3 and M4 combination, it's been mirrored with the value of I reference. So this particular magnitude would then map to a particular value of this ID1 or I reference. Okay, the same value will be mapped because of this M3 M4 mirror combination. And after that, when this current is passed on to this M1 transistor, and this value of VGS is being mapped onto the value of VGS of the M2 transistor. Okay, so in such situation, we also have to assume that this, when there is a small amount of current that is flowing through this entire structure, the drop across this resistance Rs is negligible. So we can assume that this particular drop is almost equal to a value of 0. Now due to which what are the value of VGS1 that I have got is being completely translated onto this particular structure. Okay, so due to which, just because of this relation that we have, which is a factor of k, there is a current magnification from this M1 to M2 transistor. Okay, and due to which the current through this M2 transistor, which is basically I out, gets magnified by a factor of k. So, so this gets magnified to this particular value. Okay, so this is the new spot that I have just because of the factor k that comes into picture. Okay, and this new current, which is my I out current, okay, is then again copied onto this M4 M3 combination structure, and it results in this I reference current. Okay, so again we need the help of this M3 and M4. So this kind of combination works in such a way that what happens is that the current through this M1 M4 combination will be always larger than the current through this particular path. Okay, which is the combination of M3 and M2, and due to which the initially the current through this ID2 will start rising. Okay, and that is what we could be able to see. But as it keeps rising, what happens is that the assumption that we have made earlier, that the drop across this resistance Rs, which was assumed to be equal to 0, is no more valid, just because there is more amount of current that is flowing through this particular path. Okay, and due to which I have a condition where this is no more equal to 0, and this Rs in turn tries to reduce the voltage drop that is happening across this VGS of M2, because most of the drop is taken away by this drop across this resistance Rs. Okay, and due to which the current that flows through this I out is getting normalized, or something like it gets uh, smaller and smaller. Okay, so it goes something like this, and we call this particular effect as a degenerative effect. And in that situation, one could consider that this entire structure is nothing but it's a CS amplifier with source degeneration resistance Rs. Okay, so previously, initially, it was just a CS amplifier with this diode connected load of M3. Okay, and then after we just pass on to a certain value of current flow, what is happening is that this current, previously it was just a CS amplifier with a diode connected, was being shifted from this configuration to this configuration as the drop across the resistance becomes non-negligible quantity. Okay, so there is basically a shift that is happening, and this in turn we know that the gain of the CS amplifier with a source degeneration resistor Rs will have some sort of degenerative effect at the bottom. Uh, Roughly, I could say that it is something like this, and followed by this we will have some sort of quantity that basically divides this gain. Okay, so this quantity is basically depends on the value of Rs, or basically the drop across the value of Rs, and due to which the gain through this structure becomes smaller. So whenever the gain through the second structure becomes smaller, then the current gain from this M1 towards M2 will also get smaller and smaller. Okay, so initially it was large, the current gain between this M1 and M2 was large, and that made the current flow through the second branch to be higher than that of the current flow through this first structure. But just because of this source degeneration effect, the gain is getting dropped through the second branch. It's becoming smaller and smaller, and in a way that my current gain between this M1 or between the first structure and the second structure is becoming almost similar. Okay, so and at a particular spot one could see that uh, we reach a current value where the current through this first branch, which is basically the I reference, and the current through the second branch, which is basically the I out, they both become equal to each other. Okay, and this is again one of the desired operating point that we want to have. Okay, so this is one of the operating point that we have, and so this is how the circuit works. But there is again a particular flaw in this particular circuit, which is basically um, Yeah, so before I talk about this flaw, let me talk about this operating point. Okay, so one could clearly see that this particular operating point is basically defined by the value of resistance that I choose and the value of k factor that I choose. So which means that in order to get a particular unique value of current flow through this supply independent biasing circuit, I could tweak around these resistance values and the k factor in order to get a particular value. Say for example, I need 50 microampere, then I just need to set a specific value of Rs and a specific value of k in order to get that particular quantity. Okay, so now let me talk about the drawback of this particular circuit. So as you could able to clearly see that this current equation that I have written down here uh, has can also take a value of I out that is equal to 0. Okay, so this is something which will happen when you initially assume that this I out or I reference was basically at 0. So in such situation, none of the transistors are on, and this entire mechanism will not begin. This entire mechanism of graph that I've said will never begin. Okay, and so basically the circuit, we have two circuits here, that is the branch 1 and branch 2 is basically form some sort of negative feedback or some sort of a feedback circuit, and they are being settled down. So it is not a negative feedback, basically it is a positive feedback. Okay, so there are two operating points basically to this positive feedback, and initially when this current I reference or I out is taken as 0, then none of the transistors are turned on, and due to which this entire circuit would then stay in this degenerative operating point. Okay, and that is what I just want to mention here. So that is one of the drawback that we have in this particular circuit. So one has to move away from this degenerative operating point. In order to move away, we need a circuit which is known as startup circuit that has to be added to the structure. Okay, so and I also explained without talking about the startup circuit, I said that this startup circuit has to have some sort of working principle or some sort of working principle which has to satisfy that whenever the supply is turned on, whenever the VDD is turned on, uh, the startup circuit has to turn on automatically. Okay, so it has to be on initially, and then so when it is on, it tries to induce a small bit of current either across this I out or across the I reference. Okay, so its main task is to generate a current flow through the structure. Okay, and this current flow can be even a small bit of quantity. Okay, so once it starts applying the small amount of current either through I out or I reference, then the circuit has to turn off automatically. So it has to turn off automatically. Okay, and yeah, so this is the major function it has to perform, and when we have such kind of circuit, then this circuit will function in this particular desired operating point, where we will try to obtain a single value of current through the circuit. Okay, yeah, so these were the things that we have discussed in the last class. Hope that you are clear with those explanations, and let me today I suppose to start with temperature independent reference circuit, but before that I also have to talk about one more circuit which is based on uh, the same circuit that we are talking about it, and I call this discussion as constant GM biasing circuit. Okay, so this constant GM biasing circuit, let me try to give some sort of reason why we are looking for something a constant GM biasing circuit rather than a current or constant current or something else. Okay, so the reason here is that a GM of a MOSFET plays an important role in any of the analog circuit. It is just because the GM of the mass structure basically determines the performance parameters of the analog circuit. Okay, so what performance parameter this GM actually determines can be written in a very simple way. It determines basically the noise as and the small signal gain. Okay, as well as the third important parameter that or the performance parameter that it determines is the speed. Okay, so we want all these parameters to be constant. Okay, so which means that as you could able to clearly see, the noise, we know it can be written for thermal noise in a transistor. It can be defined as 4 kBt times that of gm. So you could able to see that the noise of the circuit is basically defined by this term, which is proportional to gm, and even the small signal gain of any circuit that you take is generally written as a product of capital gm times r out. So again you could able to see that the small signal gain in turn is proportional to the gm of the circuit. Okay, again when we look for the speed, either you talk about a voltage gain or unity current, sorry, it's a unity voltage gain, which we wrote it as omega u, and that could be written as gm divided by cl. Okay, so even in this case you could able to see that the speed is again defined by this quantity gm. So we want all these parameters to be fixed when you try to design the analog circuits. And if somehow if you could able to make the gm of this analog circuit to be a constant, then all these noise parameters, the small signal gain and the speed can be defined with a specific value. Okay, so that's the reason why maintaining a constant gm in the analog circuit is more important uh, reason here. Okay, so and we want this gm uh, to be completely independent, or basically doesn't depend on these factors, because we don't want this GM to get modified because of these reasons, and such that we want this GM such that it is completely independent of any temperature variation or even the process variations or even the supply variations. Okay, so this is what we wanted out of the circuit, and let me bring back the current equation that I wrote. I guess I will just rewrite it here. Uh, that is, the I out expression is written as 2 divided by k n dash w by L of n into 1 by r s square into 1 minus square root of k the whole square. Okay, yeah. So this is what we have for the current that is flowing through this second branch. Okay, and let me also define the transconductance of this M1 transistor, which is a diode connected NMOS structure. Okay, so I could write the value of GM1 is written as square root of kn dash, and since because the M1 transistor basically has an aspect ratio of just the W by L of n, I just write that factor here, and the current that is flowing through that particular branch is basically the I reference or the uh, the ID1. Okay, now we know that this current ID1 or I reference would be equal to our I out when we are operating in the desired operating point. So which means that I'm talking about this particular point. Okay, so under this operating point we know that both these currents of I out and I reference or ID1 and ID2 are one are the same. Okay, so based on this simple expression I could rewrite this entire equation by doing some simple math. So the one thing that I need to do is simply make a small algebra and then try to find out that this factor of k n dash w by uh, L of n into the factor of 2 along with this I out, just because the I out and I reference or ID1 are same, right. So due to which one could combine all these factors and this factor basically defines a value of gm1 square. Okay, so both these expressions are same. Now based on this, I could write in terms of gm1 as gm1 square, just bringing this particular gm1 on towards the left side, and I would end up having 2 here and 2 here, so both could be multiplied to get a factor of 4, and there is an rs square divided by rs square, and then this 1 minus 1 over square root of k the whole square. And let me take square root on both the sides, and since because we are talking about an NMOS, and the gm of the NMOS will be always a positive quantity, when we take any square root on it, will be taking only the positive value out of it. So I'll have 2 here, and then rs here, and then you have this 1 minus 1 over square root of k factor here. Okay. Yeah, so as you can able to see that this value of gm1 is completely independent of uh, let me write that. So the value of this gm1 is independent of the supply voltage. That is the very first quantity that I could able to observe, and also independent of the device parameter. Okay, so I don't have any term that is related to VTH or K and dash something on towards the right side. Okay, so that is what I just mean by this particular second term. Okay, yeah. So as you could able to see that this particular circuit could be used for generating a constant GM uh, across the transistor M1. Okay, and that is what I could define over here. I have a constant GM in this particular uh, circuit. Okay, and this value of GM1 in turn is determined by the two quantities. One is RS, the other one is the geometric ratio, which is the factor K. Okay, so based on the value of this GM, based on the value of RS and the value of K that I've chosen, I could define a particular value of GM1 throughout the circuit. Okay. So now having stabilized this value of GM1, uh, it not only stabilizes, or having a constant GM1 not only stabilizes the value of GM1 throughout the circuit, which means that I'm talking about the circuit, but also all other transconductance, say for example GM4, GM3 and GM2. Okay, all the transistors transconductance are also being stabilized, just because the current flow through this structures are all derived from the same self biased network. Okay, so just because uh, the I reference and I out are all being generated out of the same circuit itself. Okay, and due to which all the GMs apart from GM1, okay, are all being stabilized, is what I wanted to mention here. Okay, now in such situation one could evaluate uh, yeah, I think yeah, so that is what I just want to mention. And uh, there is some sort of flaw in this particular circuit, just because the value of RS is quite sensitive to the temperature, but one could replace this RS with some sort of switched capacitor network. Um, Probably we'll talk about the switched capacitor network, which mimics a resistive element when we discuss about the switched capacitor circuit, when we discuss in the next coming classes. Okay, but obviously one could really achieve a constant GM1 as well as all other GMs, okay, through this network. And any circuit that I try to use, say for example, uh, whatever we have designed is just the biasing circuit, right? So from this biasing circuit, we have to take out or tap out a voltage out of this particular circuit, such that I feed this output of this biasing circuit as a kind of transistor biasing voltage to an analog circuit. Okay, now where do I tap this voltage basically out of the circuit? Is basically tapping out from here. Okay, so probably I guess I've really messed up with the diagram, but let let me just try to, yeah, yeah, okay. uh, okay, the way I be tapping out the value of VB is from here. Okay, so because whatever the voltage that I have here will give us the voltage that is required to bias any kind of analog circuit that you want to bias. And once I bias the transistors that are there inside this analog circuit, okay, the GM of these transistors will also be stabilized. Okay, which means that their GMs will also be a constant GM. Yeah, so that is the reason why we call this as constant GM biasing circuit. Okay, so hope that you're clear with this content, and let me just begin uh, with the next topic, which is temperature independent biasing circuit. And if you have any doubts, you can always come to the chat, because I've just opened up the chat screen on towards the left side of the screen, so that if you have any doubt, you can just put it onto the chat, and probably I'll spend another 20 to 25 minutes on discussing about this temperature independent reference circuit, and later I'll just have a session of 5 minutes for Q&A session through Zoom. And yeah, so let me begin with the discussion of what is known as temperature independent reference circuit. Okay, so this is a reference circuit, and what are the circuit that we have discussed before is known as a biasing circuit. And I've already said that the biasing circuit has to adjust its voltage that is generated based on the variations in the circuit. Okay, whereas this reference circuit has to generate a voltage or a current which is fixed, and it never changes with respect to any variations in the circuit. Okay, so hope that you remember those points. And what we discuss right now is the reference circuit, and I want to discuss about this temperature independent reference circuit. So now the question is, how do we generate a voltage or a current that remains constant with temperature? So in order to further proceed, let me postulate something. Okay, the postulation is that if there exist two quantities like voltages. Okay, so in this case I will just go with voltage as my quantity rather than the current. Okay, yeah, so if there exist two voltages having opposite temperature coefficients, and when we add both these quantities together with proper appropriate weights, the resulting quantity or the resulting voltage will exhibit a zero temperature coefficient. I hope that you are clear with whatever the wordings that I've said. Okay, uh, so the wording is that I have to take two quantities like V1 and V2, and in such a way that the voltage V1 is having a different temperature coefficient, and this one has an opposite temperature coefficient as that of my V1. Okay, such that when I add these two quantities with appropriate weights, and these weights is just the integers. Okay, and when we add them, we would end up having some sort of voltage which is completely independent of the temperature. Okay, so now basically you might have this question like, what is this temperature coefficient, and what I really mean by this temperature coefficient? Okay, the answer to this question is pretty simple. It is nothing but when we read the variation of a quantity like a voltage with respect to temperature, it returns us the temperature coefficient. So what I really mean is that a derivative of any quantity here. So since I said I'm just going to use the quantity as V here, or the voltage, so a derivative of this voltage with respect to t will give us what is known as the temperature coefficient. Okay, and if this derivative returns us a negative value, we call that temperature coefficient as negative temperature coefficient. And if this ratio, or if this derivative returns us a positive value or a positive quantity, then we call that dou v by dou t term as positive temperature coefficient. Okay, so this is just a theoretical explanation that I stated, but I also want to emphasize through a graph stating that what exactly we mean by this derivative. And there is also specific terms that I need to include apart from these mathematical expression of this temperature coefficient. Okay, so for that, let me try to plot a graph between this temperature and the voltage, and this can be a voltage or a current. Okay, but I'm just taking a voltage quantity over here. And whenever you have a relation something like this, where an increase in temperature results in a decrease in the voltage. Okay, so when we have such kind of situation, we have, just a second. Yeah, yeah. So as you could able to see that when you try to take any derivative out of this particular relation between this voltage and this temperature, you could able to see that there is a kind of derivative that returns us a negative value here. Okay? And we call this temperature coefficient or the derivative as a negative temperature coefficient. And in general, this negative, or let me write it as n for negative. So I'll just use the short form of NTC to represent a negative temperature coefficient, is also called as something known as complementary to absolute temperature, or in short it is called as a CTAT. Okay, okay. So what I really mean here is that whenever a circuit that has this kind of variations, where the derivative of voltage with respect to the temperature, if it returns as a negative temperature coefficient, we call that circuit as a CTAT circuit. Okay, the circuit that has this behavior, whose behavior is plotted like this, we call that circuit as a CTAT, or complementary to absolute temperature circuit. Is that is clear? Yeah. So hope that you're clear with this, and obviously one could even guess the other way around, a graph that has the opposite nature, where I have a voltage with respect to a temperature, and I have a graph which varies uh, in this particular fashion. Okay, so when you try to read the slope of this particular graph, the slope of this graph returns us the temperature coefficient, and that temperature coefficient value will be a positive quantity here, just because an increase in temperature results in increase in the voltage term, due to which it returns us a positive slope. And whenever we have such situation, we say that there is a positive temperature coefficient, and the circuit that produces this kind of behavior, we call that circuit as proportional proportional to absolute temperature, or PTAT circuit. Okay, so now that I have let me take two voltages as I stated before, and like, say for example, let us take two temperature coefficients which are opposite in nature. Okay, so when I say a temperature coefficient, I am talking about the derivatives. So I have this derivative of of this. Okay, so let us assume that this is a particular temperature coefficient, and I just want to multiply with some sort of factor in order to normalize, and also I take one more voltage source which has an exact opposite temperature coefficient as that of my V1, and when we add both these temperature coefficients, uh, just because, say for example, I have a positive temperature coefficient, and over here there is a negative temperature coefficient, and then probably the temperature or the slope of these temperature coefficients may or may not be equal, right? So in such situation, I need to apply this weighing factor of alpha 1 and alpha 2, such that when we add them together, it returns us a factor 0, right? Yeah. So now this is what we wanted, and when we do a simple integration on this relation, just because an integration over this temperature coefficient or with respect to the temperature will return us the 0 will be translated to a term which is known as a voltage, and this voltage is completely independent of the temperature, just because when you take a derivative of v reference with respect to a temperature, this derivative will return as a factor of 0, right? So that's the reason why I could state that a 0 in this uh, temperature coefficient combination returns us a voltage which is completely independent of temperature coefficient, and all of these factors will then add up something like this. Okay, just because an integral on these with respect to the temperature, okay, will return as these factors here. Okay. So hope that you are clear with what has been stated. So I'm just making an integration over this temperature, and this is the expression that I would get. So ultimately this V reference is completely independent of the temperature. Now our task is to identify what are these voltages V1 and V2 that exhibits the opposite temperature coefficient. Okay. So among various device parameters in semiconductor technology, the characteristics of BJT have proven that the most reproductive and well defined quantities that can provide this negative temperature coefficient as well as the positive temperature coefficient. Uh, so, so what I really mean by this particular statement is that if we take any BJT, it has some sort of device parameters, and these device parameters uh, has this kind of both positive temperature coefficients as well as negative temperature coefficients. Okay, and the study on these temperature coefficients are being done for a very long time, and basically one could use the device parameters of this BJT in order to get these terms, okay, which exhibits the voltage V1 and V2, which exhibits positive temperature coefficient as well as the negative temperature coefficients. Hope that you are clear with this explanation. So, so you might also have a thought process like, what about other devices like MOS? Okay, even there are studies that have been conducted on this MOSFET device parameters, and and even there are they have found some of the device parameters that exhibits positive temperature coefficient as well as the negative temperature coefficients. Okay, but still the bipolar operations or the bipolar device parameters still form the core of such reference circuits. Okay, so majorly just because the BGT has been studied for a very long time, and they have those well defined device parameters that exhibits those positive temperature coefficient as well as the negative temperature coefficients. Okay, so that's the reason why we will go with BJT transistors, and we'll discuss about these voltages that exhibits both negative temperature coefficient as well as the positive temperature coefficient. So let me begin with this negative temperature coefficient voltage that could be generated from the BJT or uh, a forward biased PN junction. Okay, so So let me take an NPN transistor, and when you forward bias, or when you have this forward biased base emitter junction, then this results in a current flow through this BJT. Okay, and let me also assume that the factor beta is set to be equal to 0, which means that the current IB is defined to be equal to 0, and we have a situation where this collector current is exactly equal to our emitter current. Okay, one can even do the same analogy. Okay, so when I under this condition, I'm just going to assume that my base and this collector are being shorted, and I have this kind of situation. Okay, or I can visualize this entire circuit of BJT with just a PN junction diode, which is again being forward biased. Okay, yeah. So both these circuits can be given in your test papers, where you may find in the place of an NPN transistor or a PNP transistor, an appropriate diode can be substituted over there. And if this diode, or if this PN junction or uh, PN junction is forward biased, then you can apply this entire theory that I am talking here. Okay, so probably I'll just see, like, if possible we'll try to do some sort of problems based on this. But as of now, either given this kind of network, or either given this kind of diode connected structure, or a diode structure in the place of a diode connected BJT, you can apply the same theory that I'm going to discuss right now. Okay, so let me write the current, the collector current, through this BJT structure, where the collector current can be defined as IS, where IS is nothing but the saturation current into e to the power VBE by VT. Okay, so let me write those notations. The IS stands for the saturation current, and the VT is nothing but our thermal voltage, and that is basically equal to kT by Q, and where K is again the Boltzmann constant. Yeah, so let me try to look back into this current equation of IS, because we want to look for the temperature terms in these collector currents. So we already found that the Vt is proportional to the temperature, so we found that, and let us look for the temperature terms inside this saturation current equation. And one could quickly write this IS, which is the saturation current, is directly proportional to the mobility of the carrier. So it's the mobility of the minority carrier, and the factor K, the Boltzmann constant, times the temperature with Ni square. And this, sorry, so this is nothing but the mobility of minority carrier, and even this Ni is basically the intrinsic minority carrier concentration. Okay. So all these mobilities and the intrinsic carrier concentration are all with respect to the silicon that we are using for the fabrication. Okay. Now, so there are a lot of small terms that I need to plug in without further explanation, because it's all semiconductor physics. So again, when we look for the mobility mu, this mobility mu could be returned is again, it's proportional to the mu naught, which is independent of temperature, times the term T. Okay, so here again you could be able to see that the mobility of the carrier, or the magnetic carrier, is proportional to Tm. Okay, and the factor of m can be roughly stated to be equal to minus 3 by 2. Okay, and again when we look for this intrinsic carrier concentration Ni, uh, so Ni square it is basically proportional to temperature cube, and then all this complicated equation where Eg stands for the band gap energy of a silicon divided by kT. So again you have a temperature term sitting at the bottom, but this term and this term, and this one is nothing but the band gap energy of silicon. Okay. Yeah, and this band gap energy Eg is closer to a value which is 1.12 electron volt. Okay. Yeah, so I'm not going to further do all this derivation. The only thing is that I just combine to see the factor of Is is proportional to some sort of temperature term. Okay, that is what I want to bring out of this mu as well as the Ni square. So I'll just write only the final expression of this Is and look for the temperature term that it depends. Okay, so one could write this saturation current Is to be equal to B, which is some proportionality constant. But what is more important is that it is proportional to the temperature, which is given with T to the power of 4 plus m, and again it also has an exponential term which is divided by kT. So again there is a temperature term that is sitting here. Okay, so in turn I could write, so based on this collector current equation, one could write down this VBE, because what we wanted is something to be proved, that we want a voltage term that is negative temperature coefficient, right. So let me try to extract the value of VB out of this expression. So taking ln on both the sides would actually get rid of this exponential term, right. So when we do so, one would end up having uh, a VB that is equal to kT, which is nothing but the thermal voltage, into the ln of hope that it is IC by IS is what we would end up having. Okay. Yeah. So having this VBE term, let me try to put that over here for better visibility. And this is what I have. And now I just want to know whether this VBE reflects a positive temperature coefficient or a negative temperature coefficient, right. So in order to read out whether the VB exhibits a negative temperature coefficient or the positive temperature coefficient, I have to make a derivative, and that derivative is basically with respect to the temperature in order to read out the temperature coefficient terms, right. So due to which, let me try to take a derivative on this VB to know whether it is reflecting a positive temperature coefficient or a negative temperature coefficient. So when we do so, uh, again the Vt is a term that depends on the temperature. So we have something like dou Vt by dou T into this Ic by Is term minus, it is something like I forgot the name, product differential rule or something like that, right. Yeah, because even this term is dependent on the temperature. So due to which I have this Vt, and when we take a derivative on this particular expression, we would end up having this Is being thrown away with Is by dou Is by dou T. Yeah. So now that we have two terms, and let me also write the final expression without doing further derivations here, but you can find it in your textbook, Razavi, all these derivations, but I just want to emphasize on only on the final point, which is the energy of the band gap divided by Q divided by T, and that is what I have here as dou VV by dou T. Yeah, so here I have two terms. Let me mark this term as 1 and this term as 2, which is the final expression, and I'll first make some sort of observation on this first expression, and later I'll just move on to the observation points on this second expression. Okay. So clearly you could able to see that there are two quantities that are sitting here. Uh, let me call this first term as A and second term as B with respect to equation number 1. Okay, and when you really see here, we know that this particular derivative of dou Vt by dou t will result in something like uh, k by kt by q. Yeah, so it would result in a value of k by q. Okay, and this quantity is pretty small just because of the fact that the value of k is in the order of 10 to the power minus 28, and the charge of the carrier which is again in some terms. Okay, so what we have here is basically a term a which is small, and we also have a term that is sitting inside this in terms of is, which can be observed as some sort of greater magnitude just because of this relation of t to the power of 4 plus m. But since because this is term is sitting inside this logarithmic scale, it basically compresses the entire quantity of is. Okay, so what I really mean here is that even though we end up having a positive value out of this a term, this positive value a, or the magnitude of this a factor, is small. Okay, so let us look for the factor b here. Now when I look for this factor b, clearly you could able to see that the value of this guy is quite higher, and just because we actually make a derivative with respect to in terms of t, so all of these factors will make the second part or the magnitude of b to be large. Okay, so just because we are trying to subtract a with b, and out of among these two factors, the factor of a, so the factor of b is dominant, the end result of this dou vb by dou t will return us a value which is basically a negative quantity. Okay, so in a particular instance, say for example, let us take a specific case where if you assume that the factor of vbe is approximately closer to a value which is 0.75 volt, and we take a temperature or the room temperature as 300 degree Kelvin, then this derivative which is dou vb by dou t will be approximately equal to minus 1.5 millivolt per Kelvin. Okay. So that is the so clearly you could able to see that there is a negative term for this coefficient, which means that we end up having a VBE parameter having this negative temperature coefficient. Okay, so that is the first observation based on the expression number 1. Now let me also talk about the observation on this expression number 2. So in this expression, clearly you could able to see that this negative temperature coefficient is proportional to a value of VBE. Okay, and also inversely proportional to the temperature. So what it really means is that when you try to plot a graph between this voltage VBE with respect to temperature, you would get a kind of cara something like this. Okay, it is not a graph that we expected where we will end up having a straight line, and we call this straight line as CTAT. Okay, the circuit that exhibits such behavior, we called it as a CTAT behavior, just because the slope of this is constant throughout this entire graph. But when we look carefully for the slope of this VB with respect to the temperature, the slope actually makes changes with respect to the value of VB that I am picking and the value of temperature that we are observing. Okay, so the slope is generally not a straight function. Okay, so so this basically creates some sort of difficulty in realizing this particular function. Just I'll try to show that. Yeah, so just because say for example, if my V1 is basically my VB and this exhibits a variable temperature coefficient, then the value of alpha 1 that I am substituting here uh, cannot be set appropriately, the weight of this always changes, okay, just because the factor VB always changes with respect to temperature as well as the VB value that I'm using to bias the circuit, okay. So this creates some sort of difficulty in defining this particular term, okay. Yeah, so probably in the next class I will talk about the positive temperature coefficient, and let me you can use this Zoom link, and if you have any doubts you can just come back. Right now I'll just stop this stream. Thanks for attending.